So our next section is going to be section 5.3, and this is evaluating definite integrals. So basically what we've been doing is we've been doing the limit definition of integrals, which involves a lot of work. So it's like when you learn derivatives, you learn the limit definition, and then it was really hard to use that on really difficult functions, and so you developed all these rules. And so that's what we're doing here. So instead of using the limit definition of an integral, what we're going to do is we're going to learn that you can actually calculate the integral. So we're still doing this. We're still trying to figure out what the integral is, but what we found out, what Leibniz found out, is that if you know the antiderivative of the function f, little f, then you can actually evaluate this definite integral without too much work. And when I say too much work, I mean less work than using the limit definition, but still quite a bit of work. So what he realized is that if capital F is any antiderivative, doesn't matter what antiderivative you're using, if capital F is any antiderivative, then you can evaluate the definite integral by evaluating the antiderivative at b minus the antiderivative at a. So basically what's happening is that if you're doing an integral, a definite integral, then you're first going to figure out what is an antiderivative of this little function f. Figure that out, plug in b, plug in a, and subtract. Now it doesn't matter which antiderivative that you do. If keep in mind that an antiderivative is up to a constant, so you can always have this plus c. But because we're doing any antiderivative, to make your life easier, you should always choose c equals 0. So I'll just choose the most basic antiderivative that you can think of, and that's what I'll plug in. So let's look at the integral from 0 to 1 of x squared dx. I know that one antiderivative for x squared is 1/3 x cubed. I know that that is an antiderivative of x squared. So I'm going to plug in 1, plug in 0, and subtract, and so I get 1/3. Now what that means for us is that if you think about the graph of x squared, so it looks something like this. Here's my x-axis, here's my y-axis, there's 0, and then let's say that 1 is right here. Then I know that the area below the curve from 0 to 1 is equal to 1/3. If you think about velocity and position, in calculus you learn that to figure out the velocity you take the derivative of position. So now it kind of works the opposite. The integral of velocity gives you the change in position. Now for notation, there's a couple different ways. Normally you can use these brackets, or you can just use a straight line. And this means the antiderivative evaluated from a to b, where you subtract the two. So that's just notation. If you draw that line, the bottom number and then the top number, it's evaluating the top number minus evaluating the bottom number. And then you can see here some other notations. So let's do an example. Let's do the integral from 1 to 3 of e to the x. So first thing, my little function, so f of x is e to the x, so I need to think of any antiderivative, and an antiderivative of e to the x is e to the x plus 1 plus 2, whatever, but we're going to make our life easier, and we're going to choose 0, so just e to the x, which means I'm going to plug in 3 to e to the x, I'm going to plug in 1 to e to the x, and I'm going to subtract. So the way I would write this is I would say the antiderivative is e to the x. I'm evaluating this from 1 to 3. Or you can use this kind of like half bracket, but I usually use the line. Plug in the top number, plug in the bottom number, and subtract. And that's how we get e cubed minus e. So just remember with definite integrals, find an antiderivative. For now, these antiderivatives are going to be super complicated. Find the antiderivative, plug in the top number, subtract what you get when you plug in the bottom number.